So, as you guys are aware, we have these companies. You see on the left side of the slide the logos representing the speakers. We have 17 industry speakers today. So get settled in. So on the right side, you are seeing the logos from the attendees. So all told, we have 30 different companies being represented today and tomorrow. And we have 5 universities. So what we think this is a great opportunity for you guys to kind of get to know each other. So look around the auditorium, look to your left and look to your right. You're looking at professionals much like yourselves that are here because you do structural analysis and optimization of vehicles. You guys also share another common interest, and that's in our software, HyperX. So like Yvonne mentioned, later today when we have the social or at lunch, be sure to introduce yourselves and get to know your colleagues. If you see the guys with the HyperX shirts on, obviously company employees, reach out to us as well. We are anxious to develop a professional relationship with you guys. So when you go back to your home offices, you'll have somebody that you feel comfortable maybe contacting directly when you have a question. So what I would like to do is to kind of step back in history of time, maybe in the last 40 years. And so myself and James Ainsworth went to St. Louis, Missouri, to Boeing Phantom Works. And we met with several people there. One, Chris Maddox, he's a senior tech fellow. He's actually Paul's boss, and Paul's in front of the room today, and he's going to be speaking in 45 minutes. But Chris mentioned that back in the 1980s, there were essentially 3 designers per 1 stress engineer. And in general, the stress guy was happy back in the days because he was able to stay 1 step ahead of his designers. He was able to answer their questions, and he was able to use his experience. He was able to use judgment. So he could inspect a part, he could define the load path, he was able to figure out what the critical load case would be and the critical failure mode, and he would analyze to that. And he wouldn't necessarily have to analyze to all the different failure modes that could exist. That's the reason he had the time to do it. Myself, I was a stress engineer. I worked on the B-2 stealth bomber in the 1980s, and everything was done with a sheet of paper, a pencil, a calculator, not a slide rule because I'm not that old. But literally, it was only maybe that thick. And a whole part was nothing but that thick of paper with hand calcs. We used 4 significant figures for the variables. And then in the 1990s came Excel, right, the spreadsheet. So not just in the financial markets, but also in the stress community in the aerospace engineering world, we started doing margin and safety calcs with the spreadsheets. And they became sort of like baseball trading cards where people were, oh, this is kind of cool. I'm going to create my own Excel spreadsheet and do a margin of safety calc. And so what would happen is over time, it became the norm, the expectation, that every single margin of safety had to be calculated for every almost load case. And you couldn't really leave any stone unturned, right? And so, you know, in a way, you jump forward to today and you talk to Chris Maddox, and he will tell you there's, in his organization, maybe a 1-to-1 relationship between a designer and a stress guy. And I would say in general, the stress guys maybe are not so happy. And why would that be? Well, they're drowning in the volume of the data, right? So designers, you know, while they have their parametric CAD systems and they're able to maybe do quicker changes to their model, in the case of the wing, you can see here the ribs and the spars. Maybe you can change the flange width of a rib. But the stress guy, he's over there busily typing away on his computer, and he's having to analyze every part to every load case with finely meshed finite element models to every element, looking at the strains and stresses in those, and then having to go to Excel and try to figure out how to get that data in Excel to do those calculations. It's burdensome, right? So yes, FEA and Excel are useful tools, no doubt. I mean, now we're more thorough in our analysis, but we're not keeping up with the designers. So the villain clearly then would be the volume of the data. It's the copying of the data from one output and pasting it to the software of another program, right? And of course, in Excel, you have all the issues with the cell math. You have different sheets, you have different references and very long formulas and these little small calculated fields. It's very cumbersome to figure that out, right, and maintain that data. What we do know is model-based engineering is here to stay, right? The idea of not leaving any stone unturned is going to remain with us, and that's a good thing. I'm not saying that. But what we need to do, what we're obviously promoting, is the use of HyperX along with those FEA models. And let the models maybe do more of the load path determination for you, and let HyperX kind of take over from there. So with that, we believe that we can get the ratio between the designer and the stress guy back to 2 to 1. And we also feel like we can get that stress guy to be happy again. He's happy again, why? He's happy because he is no longer feeling like the scapegoat for the delayed schedules, which today, frankly speaking, that's kind of the idea in the engineering community. I guess you guys would agree to that as well. He's happy because if the designer made a change in his part, he's able to disposition that very quickly. He doesn't have to spend, weeks trying to recalculate the margin of safety. He can essentially hit a button, HyperX, whether it's a new loads drop or a change in thickness of the material or a material allowable. He can get a new margin of safety out very rapidly, right? Even more so, he's got time on his hands or her hands to now study the part, look at the load path, and be able to figure out how to improve that structure. And I think when a design or a stress engineer is given that opportunity, then their job satisfaction goes up. As HyperX is an automation tool, we feel like that's what we're offering you, your chance to do the thing that you would want to do in your work. So performant automation is the essential part of what we do with our software. And as a way to kind of explain it, let me again go back in history. So after I worked on the B-2, I came to NASA Langley. I met Phil Yarrington. He's back there. He's been with me from the very start. We both worked in the hypersonics office here at NASA Langley on the hypersonics program. And our group's purpose was to evaluate contractor designs that came in from Rockwell or McDonnell Douglas or General Dynamics. These names are all changed by now. Because it was an unusual flight trajectory, the aircraft itself was unusual, things we had never seen before. And also the material systems were very unique. We had carbon-carbon, we had silicon carbide, we had metal matrix composites. Of course, we had your typical polymer composites, superalloy metals. And then we had a whole bunch of panel concepts. And these panel concepts were kind of unusual too. And we had to look at all these combinations rapidly. And we had to figure out if the airframe would fail. And we had to figure out what the weight would be if it survived. So one of the things I did from a mathematical perspective was, if you look in the bottom left here, you can see traditionally the way that models were made, and that was to discretely mesh the stringer, either with shell elements or bar elements. But the problem with that is a high element count, slowing everything down. And so I came up with a thermoelastic formulation that would accurately represent the behavior so that the global finite element model could have less elements. They could be planar. They didn't have to represent the discrete shape of the stringer. And what did that also provide us is the ability to then rapidly explore or evaluate different concepts, different shapes, without having to remesh the model. And so that was a an example in a mathematical perspective of how we were able to not produce more work for the stress engineer, but actually help the stress engineer get work done faster. And that's really what we're about. So if you look at our software over time, in the early 2000s, we already had this series of chained workflow automation. And I'll just let you guys read those for a moment. I know that all you guys that are true HyperX or hypersizer guys would agree that, yeah, these are the functions that our software performs that really do help you get your job done faster. You may say, Craig, well, okay, we get it. You know, you help automate. But I'm not convinced yet that you're really going to help the stress community get us back to, you know, maybe even a 2-to-1 ratio. To do that, I would have to convince you that we also impact a lot of structure. So if you have an aircraft, you know, it's just not a flap. It would be the acreage area, right? So if you look at the image to the left, this is a Space Launch Vehicle hydrogen tank, right? So quite a large piece of structure. So everything you see there, the metal orthogrid, HyperX analyzes, optimizes, and does the stress reports for. On the right, you're looking at the upper skin cover of a commercial aircraft. Composite, same story. We perform a lot of the analysis for that and the optimization. And so a lot of the failure modes you see in the bottom there that you traditionally would need FEA for, we're able to do that either analytically or with some kind of energy buckling solutions. We also do a lot of joints, so not just mechanically fastened joints, but also bonded joints as well. So maybe you're getting a sense that, yeah, we do pack a lot of structure. I know that Blue Origin is with us today, and thank you. And this is obviously the New Glenn rocket. And a lot of that rocket has been influenced with hypersizer/HyperX, right? You know, either by the Blue Origin engineer themselves or with the Collier engineer. But the top image is the OML, and you can see all the structures there, that these are things that we've impacted. And the second image below that would be the internal part of the rocket, and that's all the other pieces that we impact, like baffles and thrust structures. So let me change gears for a moment. Let's talk about the presentations for today. First up, after I speak, is going to be Paul DeFore from Boeing Phantom Works, and he's going to be sharing with us the use of our software on Boeing Phantom Works projects. So the image to the left, hopefully you can see the yellow. The yellow would be the bones of the structure, right? These are the major load paths. So early on in any project like this, you want to be structurally efficient, and you want to lay out your substructure in a manner that you're carrying that load as efficiently as possible, right? So you need to evaluate different layouts. In addition to that, you see that green square in the middle, and that could actually be different panel concepts. Let's assume it's a metal orthogrid. So the metal orthogrid has these local stiffeners, and as I mentioned before with the NAST, that smeared approach allowed us to very effectively represent that with a coarse model. We're doing maybe the same here at this phase of the project. But we are still able to size this orthogrid along with the bones of the structure. And, and so hypersizer was used for that. And I got a green check mark box next to HyperX because it has been a little while, but it's taking us working with our industry partner to get HyperX now approved for use on their projects. And again, Paul's going to be talking to this topic. So after we go through that phase of a project, then what happens is you make a decision on the layout of even things like the details of the panels, and you do a local sizing pocket by pocket and stiffener by stiffener analysis. In this case, this is discrete optimization because the model is discretely represented. Again, hypersizer and HyperX now approved for that. Now, the punchline is when you go later in the project, when you're looking at things like fittings and lugs, we were not used by our customer for that part of the project, so the Red X. But we are developing capability, and we are trying to position our software in a way that we are going to be acceptable to be used in that manner as well. And I'll touch this topic a little bit later. Next up, we have Blake Burke from Radia. He's going to be talking about the Windrunner, the world's largest aircraft. And as you can see here, one of the purposes is to haul these very large wind blades. This aircraft is so large that if it were laying in a football field, from nose to tail, it would go from end zone to end zone. And the wingtips would actually touch the stadium on one side and touch the stadium on the other side. And it would be 7 stories high. So it's a gigantic airplane. Michael, well, let's see. I guess what I would say about this is that they use our software to go beyond the typical New and Brune type analysis and take full advantage of the analysis methods that are native in our software. Let's see here. I think I've got my, yeah. Next up, now understand that Jonathan Russell has, Yvonne mentioned earlier, has been delayed in flight. But he is going to tell us about their use of our software on this remotely piloted drone. And this drone is even though it doesn't have a pilot, it's got an 80-foot wingspan from tip to tip. So it is quite large. Now, he will be focusing on fundamentally, again, using the HyperX methods out of the box, right? And the way that they were able to put in proprietary material and composite allowables. But in particular, he's going to be emphasizing the stress reporting capability of the software and the thousands of pages of margins of safeties report or number of sheets or pages that they produce to achieve that certification. So basically, from the beginning to the very end, to part release to certification is the story there. With us also is Don Heathcock from EOS Aircraft. He will be telling us about the role of HyperX for his project, which I'll let him reveal that. But you can imagine for a sustainability type aircraft, fuel efficiency is paramount. And because of that, that means lightweighting is paramount. So our software's purpose for now has been on to reduce weight, to do trade studies, and to look at basically major decisions like should it be metal or should it be composite. Next up, we will have Dave Paddock, now retired from NASA Langley very recently, and he will be talking about this application. It's as you can see in the images, it's a part of a space type structure. And the purple is the area that was basically of consideration. This particular piece of structure was really controlled by, say, FEA eigenvalue buckling and frequency analysis, as you can see in the right. So hypersizer was used for that. And the right image is kind of showing you the automated generated laminate families that we produce to help basically figure out what layup schedule is going to be better for reducing those frequencies. On a fun note, this is an image from SpongeBob, Patrick, and it's like the perfect representation of the shape of those the pants of the octopants and the belly and everything, right? I don't know if Dave Paddock is here. If he's here, oh, there he is. Hopefully getting a chuckle out of this. Next up, we have Howard Nessman from Northrop Grumman. he basically started from nothing at all, opening up HyperX and learning how to use it, while also creating two sort of like benchmark finite element models for a wing, one tapered, one not. He chose a mechanically fastened Z stringer to see, how he could optimize that. But he also included the study of the rib spacing as well to see the weight impact of that. So he will be sharing with us his experience for never using the software before and how quickly he was able to pick it up. Michael Peck from Aurora is going to be talking about the Liberty Lifter. It's in a DARPA program, a Defense Advanced Research Projects Agency program. The purpose is to design, build, and fly in an affordable X-plane. And as you can see in the image here, it flies low to the ocean surface, and that's to get the wing and ground effect for increased lift and range. This wingspan is 200 feet. So he's going to be talking about how they use GFEM in their department, and also the enterprise use case. You may have heard us mention this before, but we do have a specialized capability for those that want to kind of deploy it on a large scale within an organization, and we call that the enterprise. Brett Minarsik from NASA Glenn is going to be talking about basically machine learning, the Bayesian optimization technique for optimizing these cryotanks. The role of HyperX was to basically help that optimization, and the machine learning's purpose was to help create better laminate families for this purpose. Gary Wolf from Electra Aero will be talking about the EL-9 aircraft. It's a short takeoff and lift. Here, basically, they're showing the ability of the aircraft to create, I think it was a 7 times, I can't read that, 7 times greater lift than conventional aircraft. And this is what kind of allows it to do this short takeoff and lift. Relevant to HyperX is the way that they ran multiple trade studies to hundreds of load cases. And so we look forward to that presentation. Now on day 2, starting off, we have Mahesh Patel. He's going to be showing us the X-59. It's a supersonic X-plane. It was a NASA project contracted with Lockheed that then contracted with Swift to actually design that nose. And if you look at the blue there at the top, you can see the dimension to show you just how long that piece of structure is. So they used our software to do the mass, obviously, weight savings, to also filter out critical loads. But they also used HyperX for not just the acreage panel sizing, but also for the joint analysis as well. So the nose cone successfully passed proof testing, and they were very proud, and they delivered this hardware on time to Lockheed. We have Jet Zero represented today, and Logan Thomas is the first speaker. Let me just take a second. My uncle's with me today. He's an engineer as well, and he was going to only be here today. No pressure, Logan and Napsia, but now that he knows that Jet Zero is going to be here, he's thinking about coming back tomorrow just to hear your presentation. And I think that may be because we've heard, we're excited, it's the East Coast, that, let's see here, I think the governor of North Carolina says that there's going to be the largest job commitment in North Carolina history, 14,500 manufacturing jobs outside of the Greensboro, North Carolina area with an average of $90K salary. I think maybe our state, or North Carolina, is investing $4.7 billion, but they anticipate that over the life of the project, a $250 billion revenue stream to the state. So anyway, yeah, we're very excited about that. Other good news about Jet Zero, They recently passed their full-scale demonstrator CDR, and of course, the announcement I just made. With all that, I guess maybe by now you've read the bullets, so I don't need to go over those. Next up, then, will be Napsia, also representing Jet Zero. And her work uses Nastran Solution 200 aeroelasticity along with HyperX. The HyperX role basically is to provide the section cuts and to optimize to the required EIGJ stiffness terms that their elastic analysis is telling us. Now we have a panel from Bell Flight, and we have 3 speakers that are from Bell. The one on the far right, that's one of our employees, all aerospace structures engineers. Their topic is the Delta spaceship deploys HyperX at scale from conceptual design to detailed design to part release. One of the roles our company played, obviously as the software provider, but we were also under contract for this. And we did structural analysis and dedicated analysis plugin support for this project. So Kerry Cross is the engineering manager, and George is a technical manager. Let's see here if I can scroll down a minute. I don't know if you can read these or not. And Max Silva is a mechanical engineer as well. All of these gentlemen have been working for many years with a lot of experience. So I look forward to this presentation. Now, together as a team, they were analyzing the feather structure of this spaceship, right? And so many of the capabilities, if you think about it being used from preliminary all the way to the very end to detailed design, they were able to take advantage of the full suite of capabilities, including the enterprise. We will hear from this panel these particular workflows. The pie chart showing in blue the percent HyperX used in terms of the other tools that they had available. Lloyd Eldred, NASA Langley, will be talking about his use of our software, and in particular working on his structural preliminary analysis. And I can't read that, but you guys can. And by the way, we want to give Lloyd a little bit of applause because he's the guy who's done all the background work along with Yvonne and some others to make this event take place. So it's been quite a lot of back and forth between Lloyd and us to be here today. So thank you, Lloyd. So our last speaker is 96 years old, okay? And this guy is legendary. So he is the guy that wrote the textbooks. He's the guy that we learned composites from, Dr. Steve Tsai from Stanford. And he's going to be talking about his new proposed way composites are done. It's called a double-double, if you haven't heard it already. Double-double is kind of, you know, in the aerospace industry, we do quad laminates, quad meaning 0, 45, 90 ply directions. He's got a theory where you can use off-diagonal or fiber directions paired together like 20 minus 20, positive negative 70 or something of that nature. And there's some advantages to that. And so we, as a company, adopted his approach as well. So in the image to the left here, you can see in purple, that would be a tab in the software where you could click that. And you can automatically generate double-double laminates. So in the red box would be that's a thermoplastic material system. And the green box would be the number of what we call the main stacking sequence, right? So basically, we have now automated the ability to generate these. So moving from left to the middle, you can see all the laminate families we generated from this. And the far right, then, is just one example of the laminate family, as you see in the gray. And so you can have a library of these immediately made, and then you can use it with our software. All right, let me switch now to the presentations by Collier. And our presentations are mostly focused on new capabilities. So first up will be Stephen Jones. He is our Vice President of Product Development. And in particular, we want to talk about our new solver, or hypersolver. It's a capability that's going to allow us to do full multi-threading and multi-processing on high-performance computers. So it's meant to be a replacement of our current analytical engine, and we're really excited about it. So our software is really kind of broken up into three components, right? So we have the user interface, which we released about 3 years ago. That was when we provided it to the world as HyperX. And the second phase was the relational database that is the way we maintain all the data. That was kind of under the hood, and customers are not familiar or aware of this, but we can handle terabytes of data now. Now the third one, the one that we're talking about in this image here, is that solver, the analytical engine. And that is divorced now from the user interface, such that you can choose to run it on your local workstation or laptop. You can choose to run it very easily on your system, your Linux servers. Or if you choose, you can run it in the cloud on like AWS or Azure. And so, yeah, we're pretty excited about that. The other thing to mention is that it's going to be 50 times faster. And that's kind of across the board average, an aggregate number. But so maybe I should say 50 and jump up and down like a Steve Ballmer or whatever and act like a fool. But I mean, I think that's something that we really should be excited about. So what we're going to do is provide this on a trial basis to the people that are in the conference, back at your home offices. And we haven't yet figured out the licensing for this. Obviously, we're going to have to do something so that it runs separate from the workstation. But in the meantime, you can give it a spin and see how it works for you. I will get up after Stephen. I will talk about HyperExpert. It's a commercial tool we released recently. Some of you may be familiar with it already. But the purpose is to be able to not only get a lightweight solution, but to get one that is manufacturable. And this is a snapshot of the user interface from HyperExpert. And you see on the left a tree. And you see a lot of data points. Since I'm going to be talking a little bit later, I don't need to go through it in detail. But basically, the data points are completely approved designs. These are designs that have all positive margins of safety for the structure. They just simply have a different combination of variables. And the Pareto frontier then is what you're seeing with the lines, and it's helping you identify for a certain combination of, say, tooling dimensions, which one gives you the lighter weight. After I get up, August Noverre is going to be Director of Research about our CAD. He's going to be talking about how we have been continually add CAD capability to our software. And he'll be talking about, of course, the role of that. Here in the middle, you're looking at the interface from HyperX, and you can see some CAD-like geometry for a stiffened panel. And you can take that, and we do the chicken egg thing. We are like the beginning, right? We are the ones that first decide what the stiffener or profile shape ought to be. So we create the CAD, and then we allow you to import it into your favorite CAD system, whether it be NXCAD or Dassault's 3DX or CATIA. But also, we recently added the metadata as well. Metadata is a fancy word for basically the text information you see there at the bottom. But why is that helpful? Well, you can always take dimensions off of CAD parts, but it's really nice to be able to see a whole list of them. And it could be used to more readily generate the native CAD by scripting the metadata to do so. After he gets up, James Ainsworth, Vice President of our engineering, is going to be talking about how they use HyperX in their day-to-day work environment. So much like you, they also use our tool to get their work done, which is designing and analyzing aircraft. This is an image of our aircraft that James is going to show. It's a supersonic aircraft. It's defunct now. And so I look forward to that presentation. Noah Prezant, Manager of Methods and Automation, is going to be talking about two things. Basically, one, we stood up a new department in our company for helping us support customers with methods and automation. And part of that is going to be the ability to package, like in a box, the things that are required so that 10 years from now you can get the same margin of safety that you got today. And we know as engineers that's going to be necessary to do. You have to disposition a part when something happens in the field or there's a new load case or something like that. It was the realization is it's not just the code itself, but it's the maybe you had some scripts to go with it. Maybe you had some particular DLLs. Maybe you had some particular documentation on that method. Well, all of this can be packaged together so that 10 years from now you unpackage it and you're guaranteed within minutes to get the same margin. Ryan, as Yvonne talked about already, is going to talk about the advancement that we've made in high-performance composites in general. In this case, it's the high-performance biking industry. His is on the handlebar this time. So not presented, but also new capabilities. So I'm excited about this. And I like to go with this because the enormity of this launch vehicle causes a lot of challenges, right? So what happens is it's an orthogrid, and you can see in the top right, you can see basically the first dimensions you want to settle in on are the spacings. So the spacings of the webs and the longitudinal, or from the bottom of the rocket to the top, but also the spacing in the hoop direction to contain the pressurized hydrogen. And after you do that, of course, or simultaneously, is to also determine what heights and what plate thicknesses you want all of that structure to be. The red square you're looking at essentially representing just one of those little pockets, and there are literally thousands of these pockets, right, with thousands of these little stiffeners. And so the challenge is these guys have this kind of a loading environment, right? And this kind of a loading environment causes them to buckle. Now, we all know that during launch, there's axial compression in the rocket causing general instability or buckling. But we also have this other scenario happening where little tiny buckles are happening all over the place. And we have to analyze those so that we can prevent that from happening. In the beginning, it could be an analytical solution that's very efficient. But as we mature the design with thermomechanical loading environments, we want something more rigorous. So we go to an energy buckling solution like SS8. It's an industry standard, right? Well, that runs in 0.1 seconds. And you think, well, that's fast enough. But not really, because the problem is thousands of these things, 1,000 load cases, 1,000 combination of variables will cause something that runs in 0.1 second, 10 days to finally complete. And we actually worked this project, and I will tell you, our monthly Amazon Web Services, the cloud compute services bill, was well over $100,000 a month. So we were also motivated to fix this problem as well. Now, we have the 50 times faster with the high-performance computing, but another way to attack that problem is to make the individual analysis itself faster. So what we're doing is looking into machine learning. It's a field of artificial intelligence, AI, and we're creating surrogate models to be able to represent this failure mode. And as you can see in the red box here, the idea is that in the preliminary design, where you do all the heavy lifting of sizing, you can use this method. And so what it will do, since it runs about, I didn't say this, but after you train the models, about 1,000 times faster. So then you go from 10 days to 15 minutes, right? And again, then you still have the 50 times faster. So you can see that for us, everything is about fast, faster, or fastest. Or in terms of, Tom Cruise and Top Gun, I feel the need for speed. And if anyone knows me in the company, there are a lot of people in our company that are so concerned about, and rightfully, are we getting the right margin of safety? And I know there's people in my company exist. So they know that what I'm going to say is, how long does it take to run? How fast is it? And so I always push the envelope in speed. So getting back to this topic of on the right, going into detailed analysis of fittings, we are implementing an analysis for lugs. So on the left, you see an input form for the diameter hole or plate thickness. And the middle would be where you can put in the load, a lateral load, an oblique load. And on the far right would be the resulting margin of safety calcs. Is it the red obviously is telling you that it's got a problem. And these analyses are closed form and they're well known over the years. Not an issue with that at all. But the automation that we're wanting to provide is to import from CAD, like a lug, and to be able to place that on the GFEM so you can visually see where it is, and then maybe you can create an FEA element type to automatically extract load to feed that analysis, but also to take part dimensions from the CAD and be able to enter those into the lug form. And have all this tracked in the tree so that it's a bookkeeping tool already there for you in an automation perspective so that you can easily find these guys. Now, in the sense of fatigue, you may need to discretely mesh this, and you need to calculate a stress strain field around that lug. And if you do so, we are now working on offering fatigue capability. So on the left is a stress-based approach, an S&N approach, Soderberg. That's your typical kind of preliminary early fatigue assessment. We are also offering a strain-based approach, as you see to the right. And of course, the advantage of that is being able to handle plasticity and stress concentrations. And that's a little bit more rigorous, a little bit more challenging, but as an automation tool, that's our role to do that. Both methods will use the same spectrum, fatigue spectrum. So in our software, you can define that as well, and edit it. And then the idea would be now, doing the strength sizing of the lug, you can also have a fatigue life assessment as well early on. And the advantage of that, of course, is to be able to flag fatigue critical parts of your structure, but also to be able to maybe prevent that from happening from the start by sizing it out. Okay, in summary, I got the red light. I don't know how long that's been on. A little bit, okay. I'm wrapping up. Okay, Jet Zero aircraft here. This is the military version of that. The General Atomics drone, the Liberty Lifter from Aurora, the DARPA project, the EL-9 short takeoff and lift aircraft, one of many aircraft from Boeing Phantom Works. This happens to be the T-7. Space launch vehicles, such as the Virgin Galactic and the Bell Flight Feather system you see on the aft of that. EOS, sustainable aircraft. The X-59 supersonic X-plane. And all told, here are the different applications of the software that you will hear about today and tomorrow. So with that, I will end.